Welcome everyone to this session. So today we will solve this interview question, and this question can be asked for your online assessment for analog design profile. Okay. So here given that this is a single pole system and Bode plot is given. So this is Bode magnitude plot, right? And now we have to add another pole so that the uh, phase margin becomes 45 degrees, right? So let's solve. So okay. So this is called, what is called this frequency? This is called uh, gain crossover frequency or unity gain frequency. Okay, unity gain frequency. As this is unity gain, right? 0 dB. This is 0 dB, means the gain is 1, right? So this is called gain crossover frequency or unity gain frequency, or can be called as unity gain bandwidth as well. Okay. So unity gain bandwidth as well. Okay, bandwidth. So we have a only one pole system. So here the phase margin is, we know that 90 degrees, right, for a single pole system. Now actually we can add the pole in this manner. So this is our first pole, and let's say this is our second pole, and this is our unity gain frequency. So this is our first pole, this is our second pole, and this is our unity gain frequency or gain crossover frequency. Okay, and we can also add the second pole like this. So this is our first pole and this is our second pole. Okay, so this is our omega p1, this is our unity gain frequency, let's say omega u, and this is our second pole, let's say this is omega p2. So we can introduce the second pole like in this fashion or like in this fashion. Okay, but whatever, like we have to do so that the phase margin becomes 45 degree. Okay, so let's say what is going to be our second pole location. Okay, so to achieve 45 degree phase margin, we need to consider dominant pole concept. Okay, dominant pole concept. What does it mean? Dominant pole concept means the first pole is very less than the second pole. Okay, and to precisely we can say that the first pole is very less than the unity gain frequency and very less than omega p2. Okay, so this is our dominant pole concept, so that we can achieve a like sufficient phase margin of 45 degrees. Okay, so we need here to use dominant pole concept. Okay, so let's do it. And to find phase margin, we have a direct formula. Okay, actually phase margin defines the how stable your circuit is. Okay, so stability is very much important, so that the phase margin is, so the phase margin is also very important. Okay, so the direct formula is nothing but phase margin is calculated by 180 degree plus the total phase of the transfer function. Okay, total phase of the transfer function. So we know that for a two pole system, the phase margin is like negative, right? Like minus tan inverse of something, right? We know that. So now for second pole system, and there is no zero present, right? No zero, no zero. So we will directly write that, we can write that this. Okay, 180 degrees plus minus of tan inverse unity gain frequency or gain crossover frequency divided by omega p1 minus tan inverse omega unity gain frequency divided by omega p2. So this is the formula for in our case. Okay, to get the phase margin of 45 degrees. And here this minus suggests the system is lagging, right? Like we have poles, so the system gets lag when there is poles, right? So the delay will be more, and it goes for unstability, right? So more the poles, so the circuit gets like go to instability conditions, right? So now solve this. So we know that like we have told that we have to use dominant pole concept, right? Dominant pole. So if, like we know that omega u very large than omega p on, right? So what will be the value here? So this will be nothing but almost infinity, right? So tan inverse, so we have phase margin is 45 degree, right? Let's write that 180 degree here, minus tan inverse of like almost infinity, right? Like this is a very large quantity, very large quantity, and minus tan inverse omega u by omega p2. Okay, so I have write that. So mainly the dominant pole concept is this. So like the pole location is, like the second pole is not defined here, right? So we are taking this concept, like considering this concept. Okay, so mainly we are considering omega p1 is very greater than omega u. Okay, so second pole I am not considering too much here, okay, for designing purposes. Okay, so now let's do it. Like you can already say that if omega u is also, like omega u is very less, like less omega p2, so there will be, this will be like 0, right? This term, so we are not considering that. So basically this is our dominant pole concept, and we are taking that the first pole is very lower than the unity gain bandwidth. Okay, so if this is infinite, this is giving our almost 90 degree, right? So let's do that. 45 degree equals 180 degree minus 90 degree minus tan inverse omega u by omega p2. Okay, like we need to find the omega p2 location. So we, like we cannot imagine that it is like very like omega 2 is very greater than omega u. Okay, we cannot say, right? Like we have to find the omega p2, but we like in our hand, like we have omega p1 in our hand to for designing purposes, right? Like this is our dominant pole. So now we have, so this will be nothing but 45 degrees. Okay, so this will be equals tan inverse omega u by omega p2, right? So we can see that directly, this will be like tan of 45 degree is 1. So this will be 1. So we can see that omega p2 is omega u. So this is our actual solution. So we cannot take this concept. Okay, so what I am writing, so this is our location. So what we are getting here is the omega p2 location is exactly equal to the unity gain frequency, or gain crossover frequency, right? So the picture will look like this. Okay, we are introducing the pole at this node. Okay, at this node. So this is a, like this is a very important question, as we can directly find that if the second pole is located at 0 dB axis, then we have a phase margin of 45 degrees. Okay, so the picture will be looking like this, right? So this is minus 20 dB per decade, and this will be 40 dB per decade. Okay, and what I am telling previously, so we cannot take this take this condition. Okay, so we have to find this. We can take only this condition, right? So now the body plot will, what will be the body plot? So body plot will be looking like this. So this is our first pole. This is very near to the 0 frequency. This is omega p1, and here at this point we have omega p2, and from here the slope is minus 40 dB per decade. This is 40 dB per decade, and this is minus 20 dB per decade, so that we can get a phase margin of 45 degrees, right? So this is how we can approach to the question. Okay, so here the important thing is dominant pole concept, so that we can get a sufficient phase margin. Okay, phase margin is sufficient. Okay, phase margin is sufficient, and this omega p2 location is nothing but the given omega gc. the gain crossover frequency or unity gain frequency. Okay. So thank you everyone. If you like our video, you can subscribe our channel and give your valuable feedbacks. Okay. Thank you.